Actually, I'll go back to this other slide. Because last time we talked about how you make measurements on things, and like today's lab is all about this, right? You're going to be recording things, recording precision, uncertainty, that whole sort of deal. Do you want to grab one of these? So we'll be getting hands-on with this week, making these kinds of measurements. And part of the significance of those measurements and how you read those, especially analog things, we have digital scales. So for when you're getting masses, this doesn't matter. If the scale says 0.3142 grams, you write all of that down. The scale has the precision built in. So significant figures, though, and the main way that you're going to be using this is when you're reading problems or reading numbers from a problem. Those numbers are given to you with the correct number of significant digits. And then how do those significant digits change as we do different calculations? When you do your own measurements, then you'll be recording your measurements with the correct number of significant digits. But this first part, we're going to be looking at rules for counting significant digits if you're given a number. So if I tell you, or if you have a problem that has 13.301 in it, how many of those digits are significant? So in significant figures, we have a bunch of different rules. And ultimately, it comes down to which numbers are actually giving us information about the number, how big it is, how small it is, exactly. So all non-zero digits are significant. It's one of the few alwayses that you get in a chemistry class. All non-zero digits are significant. Interior zeros are significant. They're in between two non-zero numbers, so the 0 here between the 3 and the 4, or the zeros here between those other non-zero numbers. Those are the easy ones. Actually, I think this next one's easy also. Leading zeros are never significant. We never consider them for significant digits. They're only to locate the decimal point. So to tell you exactly how small this number is. All of these come before the first non-zero number. And you do this for any number. You start on the left and you work your way to the right. The first non-zero number that you get to, that's your first significant digit. And you only start counting after that. So any of the zeros that come before, ignore them. Trailing zeros, oh, that's interesting. Okay. Trailing zeros, I was expecting an example here, are significant well, they're sometimes significant. So if you have a decimal point, I'm going to highlight it again. If you have a decimal point, then your trailing zeros are significant. If there's not a decimal point, they're not significant. If there's not a decimal point, then they're ambiguous. So in this last one, trailing zeros without a decimal point, or an implied decimal point, I should say, are ambiguous. Meaning you can't tell how many of those are supposed to be significant. Because the small numbers, like numbers less than 1, we can tell that this is just keeping that away from the decimal point, right? It's got to be that small. It's in the, what is that, tens, hundreds, thousands, 10,000ths place. But for these numbers that are large, we can't tell how many of these zeros are significant because either all of them are, none of them are, maybe 2 of them are, 3 of them are, and we can't just drop any of those zeros off because it completely changes the number. So 300, right, if I just write that as 3, clearly not the same thing. I know that's no doubt, but to seen this written down, people will get to their final answer. So if I wanted to say 238,100, I'm just going to tell you how would I rewrite this so that it has 2 sig figs? Yeah, 2.4 times 10 to the 5. Has to be written in scientific notation. So really large numbers, they have these trailing zeros, have to be written in scientific notation to have the correct number of sig figs. It's either that or all of the zeros are significant. So if I rewrite this as 100,000 and put a decimal in, which sometimes can be confusing because if it's written into a sentence and that sentence ends in a period, is that a decimal or is that a period? Should be written in scientific notation, right? if I did write it this way, how many sig figs is this? Yeah, 6. But only if I have that decimal. All right, so exact numbers are a special case when we can count exact numbers of things. So if you're trying to count a number of pennies, you can see that there are 6 pennies. If I wanted to count the number of people in this room, it should be, I think today, 39, right? There's no half people. We're not unsure about the number of people in the room. We can count those discrete units. So counting pencils, another example of exact numbers are integral numbers that are part of an equation. So if you're calculating diameter from the radius, that 2 means that the diameter is exactly 2 times longer than the radius. And for certain defined quantities, so like counting, or if you're converting, we're talking about the relationship between 1 gallon and 4 quarts, there are exactly 4 quarts in 1 gallon. So if we were to use this in a calculation, which we'll get to later, but you should have some idea of, we wouldn't reduce anything down to just 1 sig fig because this is only 1 and this is only 4. When we're looking at these exact numbers, you can think of them as having unlimited sig figs. And we're always limited by the smallest number of sig figs, so exact numbers are never going to limit our sig figs. In general, I will tell you if an English to metric conversion is exact. Like one inch is exactly 2.54 centimeters. It's actually the definition of the inch. The inch is defined based on 2.54 centimeters. But something like 2.2, I think maybe 2.22 equals 1 kilogram. That would be not exact. Or whoops. So sometimes conversion factors can affect the number of sig figs that you have, this being an example. But for those ones that cross from one system to another, I'll tell you. For other things, like metric to metric or English to English conversions, those are almost always exact. Metric to metric is always exact. So if I write, just to do another example of that, 100 centimeters equals 1 meter, this isn't ambiguous because there's no decimal, because it's got trailing zeros. This is an exact conversion. 1 meter is exactly 100 centimeters. So unlimited sig figs for that one. Okay. The spot is really squeaky. So I'm not standing on it. Okay. For A, how many sig figs? 3. For B, you want to say 1. It's exact. Infinite. Unlimited. So yeah, 7 pennies, 7 people, 7 dogs, 7 pencils. We're counting discrete units of a thing. With a ruler or something, it's depending on how far you can zoom in, that's when you get sig figs, really. When you're counting a number of pennies, it's unlimited. All right, how about C? 3 sig figs. For D? 2 sig figs. E? 5. And then for F, ambiguous. We don't know. And that's because, yeah, some of these zeros might be significant, some of them might not be. This one as written would be ambiguous. You do another example. How would I write this with, say, 4 sig figs? Yeah, I think you said 21.00, but that would be, yeah, so here, oh no, sorry, yeah, you're right. 21.00 times 10 to the 3 would be 4 sig figs. We should say meters. Now, scientific notation allows this. You could do this. You could write it as 21.00. that is okay. Generally, unless you have a specific reason for doing that, you would write it so that whatever portion here is in front of the decimal, or actually, somebody on Discord asked about this, and I thought it was a typo, mantissa. No, this is actually the technical term for the part of the number that has the significant figures, or the significant digits. So this 21.00, this is the mantissa. I didn't know that. Yeah. So yeah, that's what I was saying, is that if you have a specific reason for doing this, like maybe I want to compare this to, I'm going to go over here and rewrite it, because this is in meters. I don't know, we're comparing the length of two roads or runways or something, I don't know. And I'm comparing this one that's 21 times 10 to the 3 to one that's maybe 9.00 times 10 to the 3 meters. This is very easy to see that, oh yeah, that one's bigger than this one. The normal way that we would write these in scientific notation would make this one 2.100 times 10 to the 4, 9.00 times 10 to the 3. So if you're looking at it carefully, familiar enough with scientific notation, you look at this one, 2.1, you look at this one, see 9, this is to the third, this is to the fourth. So actually this number is bigger, even though the decimal portion, or the mantissa, looks, if we weren't looking at the scientific notation, looks like it's smaller. So in this class, generally 1 to 10 for this decimal portion, because, I don't know, we're not writing up, I mean, you're writing up lab reports, but this is the thing, like if you're doing a report for a group or as part of your research or something, you might pick numbers to make it at a glance more comparable. So yeah, generally 2.100 times 10 to the 4 meters is the more acceptable answer, the better answer. Okay, any other questions about sig figs or scientific notation? No? Okay, so when we're doing calculations, sometimes the calculations can change the number of sig figs. Sometimes we're using multiple different measurements collected with different instruments. So like the pre-lab for tonight had you do this for, was it question 5 or 6? And it said, if you calculated the density of water using a graduated cylinder, I think it was a graduated cylinder? Or maybe it was a volumetric pipette. So you'd get a measurement of 25 milliliters, and if you used an analytical balance, that would be 25.0000 grams. So I've got two numbers collected in one case from the analytical balance, and then I think it was a volumetric pipette. And they didn't say specifically it was a volumetric pipette, but with that precision, I'm assuming. So each of these has a different level of precision. This one's got 4 decimal places. Or if we were counting total sig figs, how many sig figs? 6. So we start with the first non-zero number. 1, 2, decimal means that we count the trailing zeros, so all of those are significant. So that's 6 sig figs. But our volumetric pipette measurement only has 4 sig figs. So this next thing that we're going to talk about is when we do mathematical operations. So if we want to calculate density, be the mass divided by the volume. How do we know how many sig figs come out of this calculation? Yeah, since we're doing division, this will be the lowest number of sig figs. You had a question? Oh, yeah. So it would be division in this case. Yeah.
Would we make the milliliter?
You could. I guess in this case, usually when we're talking density, it's grams per milliliter or grams per centimeter cubed. Not technically wrong to do grams per liter, but since a gram, I guess you can see here that 1 gram and 1 milliliter represent, at least in the case of water, and in most things, roughly the same amount of a substance, at least if we're talking about density. So they're on the same scale, we might say. 1 gram and 1 milliliter on the same scale. Whereas if we did grams per milliliter, grams per liter, a liter is 1,000 times larger than a milliliter. So we've got a disparity, I should say, between the scales of our measurements. Usually, at least in questions that I write, and Alex is usually very specific about this, I'll give you the units that I'm looking for in the final answer. And Alex is usually pretty good about that. Or it'll tell you that you didn't get the right units. So anyways, yeah, multiplication and division. The key here is just remembering the difference between significant figures, and when we get to addition and subtraction, decimal places. Multiplication and division, we're going to be looking at the smallest number of sig figs. Like in that previous example, we had 6 and 4. 4 is the smallest. Our final answer keeps 4. So here in this calculation, our first number has 4 sig figs, 5 sig figs. This last one only has 2 sig figs. So when we do our calculation, the calculator will spit out something like 6.7208. And then the way that we pick which sig figs we keep, so you start with the first non-zero number, and that's your first one. The one after that is your next one. So here we keep just 6.2. So you can see 4 sig figs, 5 sig figs, those are pretty decent measurements. But because this one measurement has only 2 sig figs, it throws out the precision of your other measurements. So especially in lab, if it says to use the analytical balance, and maybe this is a good time to just mention this, it says something like to the nearest 0.0001 gram, that's saying use the analytical balance, use the one that has precision all the way down to the 10,000th place, the 4th decimal place. So similar with this next one, 5 sig figs, 3 sig figs. So from this answer, and this is the thing that I've seen a lot, my first non-zero number is my first sig fig. So we don't count the leading 0. We do count 6, 2, and 6. So that's why the final answer here is 0.626. You can see some of this is importance in another one of the pre-lab questions, where it has you do the calculation, but if you were, says, what if you were, all of your measurements were low by 0.01 gram? So you go through and you redo the calculations, and it's a little bit different. But if you're counting the sig figs based on the precision of the things that you're using, your measurements, that difference actually occurs after that point of significance. Okay, so multiplication and division. Let's use sig figs. When we go to addition and subtraction, like I said, the thing you got to remember is the difference between sig figs and decimal places. So here we're only talking about decimal places, smallest number of decimal places. So the decimal places are the places after the decimal. This is the only time that we count leading zeros. But we're not saying that this has more sig figs. We're just saying that it has 2 decimal places. And if you're doing this by hand, probably the easiest way is to line them up like this and say, okay, if I draw the line here, basically, because that's the smallest number of decimal places, I'm going to drop the numbers that come after this, unless it rounds up. So this is 3 decimal places, 2 decimal places, 4 decimal places. And so we only keep 2 decimal places. And again, it doesn't matter that before the 7, there's nothing there. Okay. How does everybody feel about that? Okay. We're going too slow, too fast? Good pace? Yeah? All right. Let's keep trucking. Rounding rules. Hopefully you've seen rounding rules before. They're not tricky. If the number that rounds off, so let me grab an example. All right, so 5.679, and we were keeping, in this case, one, maybe I should just underline the one decimal place that we're keeping. We're keeping the 6 that we need to remove or round there. After the 6, if the number is 5 or higher, we round up. If the number is 4 or lower, we round off. We don't try to avoid saying round down. We just drop it. So in this case, because it's 6 and then a 7, the 7 is higher than 6. And it doesn't matter what comes after that next digit. It doesn't matter that this is 9. This could be 9, this could be 0, this could be 1. Doesn't matter. We only look at this digit. So we round that up, and that's how we get the 5.7. Oh, yeah, so this last note here is when you're rounding these large numbers, so I'm going to round this to 3 significant figures. Which digit am I going to round off at? Yeah, so we start with the first non-zero one. So that's 1, 2, 3. So we keep the 9, and then because the next digit is a 3, do we round up or round off? Round off. Round down. It is going down because we're making it a 0, the 3 is 0. But so this would be 24,900. And what's the problem with that? There's either too many, or too few, or it's ambiguous. So we don't know how many sig figs there. And of course, we just did this. It says 3 sig figs right there. We know, but the problem is that when this number gets written down in a report or something, and then you give it to somebody else, give it to me, I don't know how many sig figs you intended for that to have. So when you're rounding to the tens place or higher, that's when you can have trailing zeros, and you can have this ambiguous situation. So this needs to be scientific notation. So 2.49 times 10 to the 5. Sorry, times 10 to the 4. Okay. Honestly, you're never going to be wrong if you put it into scientific notation, at least with me. I'm not sure how Alex would handle that. Alex will sometimes do things, I don't know, not necessarily wrong, just sometimes weird. Actually, this is a good time to talk about. If you get an answer and it's, I don't know, 31, and you want 2 sig figs, you're like, that's 2 sig figs. I don't need to put it in scientific notation. It's not ambiguous. You put that into Alex. Some of you are smiling already. Do you know what Alex is going to say? It is annoying. Put the decimal in. I don't know, maybe you'll have a better time actually if you just do everything in scientific notation. Because you'll always have a decimal,
Sometimes
pretty much.
It's you. Sometimes I'm like, remember, decimal place when you have something that's amazing.
Yeah,
And I was like, when are we going to need to do that? I'll do it.
yeah.
It won't give you the scientific notation option.
Oh, like the options to do the, yeah. So just remember, this is what it's talking about. If it gives you that error about putting in a decimal because it's ambiguous. I'm not going to get into. There's a lot of things I like about Alex. I wouldn't be using it if there weren't things that I liked about it. There are some things that are a little bit annoying. Okay, so I think we're good on rounding. Again, if you have any questions on any of this stuff and you're just too embarrassed to ask in front of everybody, which by the way is probably fine, there's probably somebody else who has the same question, come to my office hours, ask Tab, send me a private message on Discord, or send me a message on Canvas or something. I'm happy to answer it. I'm not going to read that and say, ha, look at that, and then show it to everybody else. I'm not going to do that. I will try and give you a good answer. Because I want you to learn. And if there's, I don't know, stuff that's early on that you feel like, oh, that's too basic to ask a question about, no, let's just get past it. Let's get on to the other stuff. Anyways. Okay, so rounding and multi-step calculations. Happens all the time. But do not round intermediate steps. So if you do a calculation, we're not going to round until the very last answer. Now, when we do multi-step calculations, especially stuff, actually, almost exclusively stuff that has a mixture of multiplication, division, and then addition and subtraction. Also, you're going to have to work in steps, and then at each point determine how many sig figs are in that step. So a good way of keeping track of what your significant digits are is to underline them. Generally, I will underline all of the significant digits. So in this example, I'm going to underline this one also, saying that the 4 and the 7 are significant. So when I go on and I do my next calculation, we would say that 3.78, that's 3 sig figs. 5.903, that's 4 sig figs. How many sig figs do I have here? If this number was by itself, it would be 3. But because it came from this calculation, it's only 2. So we say, because this is from another calculation, this would be 2 sig figs. So I do the math, my calculator spits out more sig figs than I need. I say, okay, 2, 4, 3. 2 is the smallest number of sig figs. So 19 would be the answer. Ah, it is 3 sig figs.
Oh, but we're doing decimal.
We're doing subtraction. So yeah, so it's decimal places. Yeah. So I think that's the thing that trips people up between those two. Decimal places. Sig figs, be counting everything. Decimal places, it's just well, I say everything. I hope you know what I mean. Not everything. Right? Anything in front could be a significant figure. Decimal place is just after the decimal. You can keep all of the digits in your calculator pretty much always. So if you, for whatever reason, you don't like your calculator, you think it's working against you, you think it's trying to undermine your learning, you can at least just write more digits down. You don't have to write out all, I think most calculators will keep like 14 or something. You don't really need all 14, and you can test this yourself. It's similar to that question in the pre-lab where it's, well, if you just made it like 0.01 smaller, how does that change your calculation? If you keep 2, 3, 4 extra, probably going to be fine. I do want to just really quickly show you on this. All right, so this is my favorite calculator app. It's free. It does have like ads, which is like a single banner like at the top or something. And then it's a choose your price to not have to have ads anymore. So you can pay like $1. I paid $10 because it's super cool to have this app. So if you do a calculation, and let's do that one that's there. Or actually, whatever. I'll do this. Let's do 2 times, this is a cool thing that you can do if it's on a computer. Right, can I? Yeah, 2 times pi, right? So if I do 2 times pi, that's going to give me, because pi is unlimited digits, gives me this really long number. But let's say I only need to keep 3 of those. You don't need to write this whole thing down. Most calculators, if not all scientific calculators, will have some option like this, where you can do second, and you can do answer. So if I do second, and then this, A and S, it's over here above the minus, that will just grab the previous answer. So you can use that to just keep all the digits in there. And so if I hit enter, then it'll just give me that same number again because I didn't do anything to it. The other thing you can do on most calculators, including the one that I recommended, just trying to make your lives easier, including this one, is there's this STO, that's short for store. So say you want to save a number. So I do this calculation. The next thing's really complicated. I don't know where I'm going to need it inside of that whole thing. Or maybe I'm going to need it later on. I got to do some other calculations first. You could do, I'm taking a little bit of a risk here. Okay, yeah, cool. That's how I thought it would work. You hit store, and this works a little bit differently on different calculators. On a TI-84, you have all these letters, A, B, C, D, E, F, G. You can use those to all store variables. On this calculator, there's one button that's like X, and then it's got Y, Z, T, A, B, C, D. If you keep pressing that button, it will cycle between all of those different variables. So I can do store second, or not second, sorry, alpha A, hit enter. And then I could do, I don't know, 16 plus 7, And then I say, okay, by the way, yeah, if you just hit any operator, so plus like that, it'll grab previous answer, automatically inserts that in there. Now I want to do 23 plus my answer that I saved as A. So I just, over here, I hit alpha, I hit A, hit enter. And that'll stay in there until your battery dies or you clear it. Or replace it with something else, right? So use your calculator. It's got some great stuff that it can do. All right. Okay, a little sig figs practice. Now would be a great time to use or try out that trick that I just showed you. What slide are we on? 32. Okay. Who's got the first one?
3.8 times 91.
Hmm.
My calculator. I don't think my calculator myself.
What do you mean?
I inputted the exact sum. Is that right?
So there is a mode on your calculator that will put everything into scientific notation.
I didn't know if that was right because it,
Yeah, if you switch the mode and then just hit enter again, it should just spit out the same number. And
yeah, I think it's right. Yeah, I got that.
yeah, yeah, it's always going to round some because the digits might go on forever. Yeah, so you said 3.8. So two ways that we could write this one. One would be in scientific notation. One would be not. How many sig figs? Oh, wait, your calculator rounded it to just 3.8?
It's at 3.8099. You got 0.38087.
Interesting.
Give me one more. I'm going to see it.
Anyways, this is what you should have gotten something like this. How many sig figs do I keep? 3. Because this has, what was it, 6, 4, 0.0301 is just 3 sig figs. Because these are leading zeros, so we don't count those. So this should be 0.381. So we didn't have to go stepwise on this one because it's all multiplication and division. Just count the smallest number of sig figs. As long as there's no addition or subtraction, doesn't matter. We just keep the smallest number of sig figs. We'll tell you this now. Majority of calculations that we do in this class are multiplication and division. There is some addition and subtraction. Okay, so anybody got B?
133. Yeah.
Does everybody agree? 133? Whoops. Yep. Stupid calculator. I got something slightly different.
I didn't subtract as well.
Ah, okay. Now, do we need to go stepwise on this one? One person nodding yes. So do we need to like, do we have that in the previous example? So like in this one, we did this step first, and then brought that down and did the other steps. Yeah, so for this one, because it's all addition subtraction, we don't have to. I got 120.961. How many sig figs should my final answer be? How many sig figs? We keep the fewest number of decimals. The fewest number of decimals is 1. This is 1 decimal. So that will be my last sig fig. So then the non-zero numbers and interior zeros that come before that, those are also sig figs. So our final answer here has 4 sig figs. So that would be, so when I keep that 9, the next digit's 6, so I got to round up. Would love to take more time on these, but okay. Let's see. This one we do need to go stepwise in order of operations. I'm just going to write it all down. So after my first step there, what's the first step? Yeah. We add those, do the parentheses first. How many decimals do I keep? 2. How many sig figs does that mean I have? 4. That's 4 sig figs. Now we keep the whole thing, and we do 2.5, whatever that is, times this, divided by that. And that would give us this number that I wrote, assuming I didn't make a mistake. Everybody else get that? So how many sig figs should my final answer be? Yeah. This is 4 sig figs. This is 5. This is 4. So it's 1 squeaky floor. All right, so last one. Do you have to go stepwise? Yes. So we have multiplication and addition. So this is 3.603 plus 4.811. But the 3.603, how many sig figs does that have? Do we count leading zeros? Just 1. 0.3 is just 1 sig fig. So this would be just 1 sig fig. So if I do this now and I do 3.603 plus 4.811, that will be 8.414. Write that a little bit neater. 8.414. So how many sig figs does my final answer have? Just 1. We keep, because I underlined this 3, so that means it's my only significant figure in that number, meaning that these decimal places aren't significant. So this one's got 3 decimal places. This has 0 decimal places when we're thinking about significance. This would be 8. This one's also a good example of why we can't round in between. So if I take this 3.603 and I'm stopping at the 3, if I round this, it becomes 4. And now I've got 4 plus, actually here, let me do this in red because it's wrong. So this, if we round it, becomes 4. Now it's 4 plus 4.811, and that would be 8.811. And if we round that, it'd be 9. So in this case, because partly because we have this, which is terrible in terms of sig figs or precision, it makes our answer off by 1. Does that make sense? Don't round in between calculations. Won't always cause you to be off this much. Sometimes it'll cause you to be off by more. Okay, that's from last semester. That's from last semester. Okay, the difference between precision and accuracy. I do slip up a lot and say these interchangeably, so I have to correct myself. Because it's been a year since I taught even Chem 1. We don't really talk about it in OChem. Okay, accuracy determines or is a measure of how close a value is to the true answer. This is the thing that comes up a lot in science is like, what is the actual value? Most of the time you can't know what the actual value is, but you can usually figure it out if you're close. Accuracy refers to how close. Precision refers to how close to the same spot all of your measurements are. Doesn't matter if you're not close to the right answer. All of your measurements are falling really close together. You're very precise, but very inaccurate. If we consider the results of these 3 students, repeatedly weighted lead block, known to have a true mass of 10 grams, which student was the most accurate? Student C. We look at their average and see their average was the closest to the true value, and even their values here, their different trials, those are pretty good. All right, so which student was the least accurate? B. This could be a little bit tricky because you're like, wait, how do you even tell? So like this, we know the true value is 10. So how far away is student B from 10? 0.21. Don't feel bad if you have to do a calculator with that. I spent most of my time just now thinking about what that was going to be. So 0.21, this one's easier, it's higher because it's 0.13, right? So this is higher. So this is the, student B is the least accurate. Oops. Now, was student C also precise? So that's how close their values are to each other. Yeah, right? Their values are all right around 10. Student B, I think in this case, did the worst on everything. Oh, I don't know. You think student B or student A is less precise? Huh?
I said student B and C are the same.
B and C are the same precision?
No, the most is 0.5 off, 0.05 off.
Yeah, so similar precision. Also, do you want to point out, hard to tell from just looking at numbers, right? This is why we have other ways of visualizing data. There's a much better way to visualize the data. So yeah, student B was as precise as student C. A little bit harder to see because it's not so close to 10, I think. But you can see student A, now when we plot these out on this sort of bar chart, you can see that all of their values are way different from each other. You can also see that these values are pretty close to the sort of scatter or difference around this average line to student C. And so when we're talking about precision, how close these are both precise. We're talking about accuracy, how close to the true value. This is accurate, this is inaccurate and imprecise. Okay. So there are different types of error. Yeah, different types of error. Usually, like random error is going to be what we'd say is evenly distributed. So you have as many, if you take a whole bunch of measurements, you have as many measurements that are above the true value as you do as below. And that's just because it's completely random. Systematic error, so like for student B, systematic error is usually too high all the time or it's too low all the time. Or it could be kind of anything like student A, where they had values all over the place. Can anybody think of a systematic error that you might make when weighing something?
Some of it fell out.
Yeah. So if you dropped some and then you went and you weighed it multiple times, probably going to give you a systematic error. Right? It's going to tend to make it too low. Another one that I was thinking of is if you put the weigh paper on and then you don't tear it, and then you try to weigh something out. Tablet tub, like she was triggered. Yeah, that would be an example of a systematic error because you get eddy currents from the heat above whatever you're weighing. Random error most of the time is going to be like on electronic scale, it's just like electronic interference, or it could be usually the balances have to be on a counter that's really heavy because that way it has a lot of inertia, meaning it's hard to move or it doesn't move a lot. Sometimes that's not the case. Like in this room, because the floor is so squishy, if I put a scale here and you guys were walking around, or even if somebody was just bouncing their leg, that scale's measurements would just keep going up and down and it would never settle. Okay. All right, we're going to talk about problem solving. Most of the problems in this class are unit conversion problems. And the more that I teach chemistry, the more that I think it's not the unit conversions that are usually the difficult part. It's the word problems that are the difficult part. Because once you can figure out the number that you're starting with and the number that you're trying to go to, it's just plugging in a series of conversions to get there. The hard part is figuring out what am I starting with, what am I trying to end with. And generally in this class, that will start out simpler, and then we'll have more and more ways to calculate things or more conversions that'll increase that level of complexity. Sometimes there will be specific equations. So we'll talk about like heat capacity. That's got a specific equation. But we're going to really focus on this idea of dimensional analysis. Yeah, that's what I was going to say. This dimensional analysis, this idea of using these, we've got unit conversions. The dimensional analysis also is sometimes called unit analysis. We're using the units to do the analysis. You should always include your units. And I know because I never wanted to. And I made a lot of mistakes because I didn't write units in. Because if you don't write units in, you start putting conversion factors in upside down. But you can't tell because you don't know what units you started with. You think you know. That's the problem. The problem is that you think you know what you're doing. You think that you're setting it up right. And you're very close. But writing those units are just a reminder to yourself that I need this quantity and I'm converting it into that quantity, or I need to use this conversion this way. It also helps a ton when you go back to look at your own notes and stuff to know what you were doing. Or it helps me not have to do so much detective work to try and give you feedback. Figure out numbers that you're adding, dividing, multiplying. Our units, this idea of dimensional analysis really revolves around this also, that units work like algebraic quantities. Meaning that if I have something like x, I mean not use x because I'm going to use, so if I do y times y, that would give me y squared. It's the same thing with units. If I do centimeters times centimeters, that would be centimeters squared. If I take y squared, or if I take y divided by y, anything divided by itself is 1. It's the same for units. If I do centimeters divided by centimeters, that's centimeters is divided by itself, becomes 1. And so when we say it cancels out, we're saying really that it becomes 1. And now I don't care if I multiply or divide by 1 because it doesn't change anything. Sometimes it's just trying to get out of these common things out of the way. Let's say I'm trying to convert from, actually here, we'll use this next example. So if we're trying to convert things, we're going to have these conversion factors, or which are the relationship between these units and that units. This conversion factor is saying I have a distance, and that distance in centimeters is 2.54. In inches, it's 1. But they both mean the same distance. So it's two ways to describe the same thing, and we're saying that this quantity is equal to this quantity. So when I write something like, lost my train of thought, 2.54 centimeters divided by 1 inch, this really means, this is not going to be 1 inch on the projector because it's way bigger, right? This distance is 2.54 centimeters. This distance is 1 inch. If those are the same, this is being divided by itself. So really it means 1. And so if this is just 1 and that's just 1, then it doesn't matter if I write it the other way, right? If I write 1 inch over 2.54 centimeters, means the same thing. So that's why we can take these and we can flip them upside down. Because at its core, it's describing to us a distance. And those distances are the same. So divided by themselves, it's 1. The usefulness, of course, is not that we can write it this way, because it doesn't really work by itself. But let's say I have 31 centimeters, and I want to convert that into inches. So very often I will write out stuff like this. So 2.54 centimeters goes on the bottom, 1 inch on the top. And I'll say, okay, centimeters cancels out with centimeters. And I'm doing an extra step in my head because this is going to be 3.1 centimeters times 1 inch on top. And so I'll have centimeters, inches, divided by centimeters. So centimeters divided by centimeters, those cancel out. Because this is the same thing, centimeters times 1 inch over basically the same thing. If I did 31 x times 1 y divided by 2.54 x, right? X divided by x, centimeters divided by centimeters. So those will become, that part of it will become 1. And so really this is just 31 inches divided by 2.54. So 12.2047. How many sig figs? 2. Because this is exact, this is 2, so it should be 12 inches. Okay. So that's why this will be like the main setup for most problems, because we're just writing out like, how do I convert this? Centimeters cancels out with centimeters. Put this into a more general way, right? Given unit times, this is the conversion factor, desired unit over the given unit, it's going to equal the desired unit. So how many centimeters are in 12 inches? Unintentionally did that. Just picked 31. But to say it more exactly, I say 12 inches, that's our given unit, times, and we know the conversion factor is 2.54 centimeters, that equals 1 inch. So I look at my given units, I say, I have inches, I want to cancel out inches, so I'm going to put this part, the 1 inch part, that's 1 inch of my conversion factor on the bottom, and then the other part has to go on top, because that's the part that's equal. Otherwise, it's not 1, it's not a conversion factor. So it's 30.48. Ooh, and this is a good one for sig figs. How many sig figs? What's the smallest number of sig figs? A little bit of a trick question.
Everything's exact.
This is exact. This, if it was 12 pennies,
Sorry, wrong.
yeah. So this is 2 sig figs. These are exact, so that's unlimited. So my final answer would have how many sig figs? 2. I'm sorry, I didn't write units in. Can I leave it like that? Ooh, who said yes? It's okay, actually, I don't want to call you out. Technically, like that, you could leave it like that, because I'm saying there's a decimal, so trailing zeros are significant. I'm saying that 0 is significant because I want 2. Now, the better way to do this is scientific notation. Feels weird. Times 10 to the 1. A little bit, yeah. A little bit. They both work. Okay, let's talk general problem solving real quick. It really does boil down to just this sort of conceptual plan. The given, you figure out, okay, once you know what you're given and what you're going to find, beginning point, end point, this is like Google Maps. Now you're making the maps. Or you're drawing the route yourself, right? If you drew or put a dot here on campus and I put a dot at home, the conceptual plan is how you get between those two. And we're doing that with math. You want to find your given, almost always going to be, how do I phrase this? It's usually not going to be a conversion factor. Meaning something with per in it is probably going to be a conversion factor, right? Miles per hour is a conversion factor between the miles you go per 1 hour. Centimeters per inch, miles per gallon, that kind of thing. Dollars per yard if you're buying fabric. Per is usually an indication, it's not always, it's usually an indication that's going to be one of your conversion factors. You're going to use that, but it's going to be part of your conceptual plan. But first find your given, and then this is usually easier to find. Identify the endpoint, what you must find. The question will say, calculate this, but in whatever units, right? So then what you must find. Now the conceptual plan, the better that you get at conversion factors, the easier that this part gets. But this will really set you up And most of the time you can do it with just units. And then you write everything out, plug it into your calculator, hit enter, double check it. This last one, does the answer make sense? If I'm asking you how many grams are in 1 liter of water, and you do the calculation wrong and you tell me that it's 1,000,000 grams in 1 liter of water, 1 liter, try and find things that are like everyday life. Like a 1 liter water bottle is like this big. 1 gram is like a penny weighs more than 1 gram, maybe about 1 gram, 1.5, right? So 1,000,000 grams is 1,000,000 pennies. It's going to be very heavy, even though it's small. So that can be a little bit more difficult to like work on that sort of intuition for whether a number makes sense or not. But usually your units, if you set it up correctly, can help. Okay, so we're going to convert from 288 centimeters to yards. I know we're almost out of time here. So what are we given? Yeah. We say given. And what do we want to find? Yards. Is that a pirate's favorite unit? Sorry. Yards. So centimeters to yards. So this is the beginning of our conceptual plan. It's a lot easier if you are working on a digital medium because maybe this is going to take way more steps than I think it is. I can move it away. If you're ever worried, just start with them super far apart. It's fine. Okay, so how do I do this conversion? Anybody think of a route that we can take? What can we convert centimeters into? We can convert it into meters, but does meters get us closer to yards? Depends on the conversion table that you're looking at. But we've been using inches a lot. How many inches are in a yard? 36. So if I can convert centimeters into inches, I can do inches into yards. I can show you later if you're interested, right? So we do centimeters into inches, and then from inches, we can take that straight into yards. And you might want to write in here what those conversion factors are. Because we're starting with centimeters, 1 inch over 2.54 centimeters. And then this will be inches on the bottom, 1 yard on top. But don't be afraid to like map this kind of thing out. If I do this conversion, then I have to do another conversion, but does that eventually get me to the end? Because there's, I don't know, probably an almost infinite number of ways that we could do this. We could go from centimeters to meters to kilometers to miles to yards to feet to, or I guess to yards, right? So when we're setting this up then, now I've got my conversion factors written in. I can add my 288 centimeters, that's my starting up here. And I'll say this a lot too, you multiply across the top. If they're ones, you can ignore them, and then divide by everything on the bottom. I'll show you actually with the calculator on screen. Oops. There you go. 288. So, right, multiply by everything on top. I'll just put them in there just because. Times 1, divide by everything on the bottom. So 2.54 divided by 36. In theory, if I press the button. Divided by 36. Multiply everything on top, divide by everything on the bottom. Because for multiplication and division, the order of operations works out. So 3.149606. Can hide that. Yards. I guess it's given away up there, but why is this 3 sig figs?
288.
288. Our other conversion factors are both exact. I've said a few times now that this one's exact, and this one's English to English, so that's exact. Yeah, 3.15 yards is the answer. And we didn't get to metric prefixes. Okay, we'll have to finish that up on Wednesday, quickly.